The purpose of this screencast is to show you an example calculation problem using the heat of vaporization. The heat of vaporization is very similar to the heat of fusion. However, in this case, now we're talking about a phase change that has to do with boiling, evaporating, or condensing. Condensation is just the opposite of the boiling process, where you have gases coming together. Those particles are getting closer and closer and turning into a liquid. It takes a lot more energy to boil water than it does to melt an ice cube. So for that reason, we're going to always recognize that for any individual substance, we are going to have a larger heat of vaporization than our heat of fusion. We can see that in our example with water here. The heat of vaporization, HV, is much, much, much larger than the heat of fusion. And that aligns really well with the way that we've been thinking about these changes in phase so far. For this problem, we're going to take a look at our temperature versus time graph first. The problem tells us that 4,250 joules of energy is removed from a sample of water vapor, condensing it, that's a gas to liquid phase change, into water. What is the mass of the sample? So we know that the boiling process and the condensation process will both happen at 100 degrees Celsius. So on our graph, we'll label 100 degrees Celsius, and we're going to show a flat line on our heating curve that represents that process of the gases turning into liquids. Those particles are coming closer together. We will not see a change in temperature during this time. For this example, we have a certain amount of thermal energy. I would say that we can assume that our gases are pretty darn high in temperature at 100 degrees Celsius. So I'm going to put 3 blocks of thermal energy to start. I'm starting as a gas, water vapor, so I'm going to have 4 blocks of phase energy. And as always, since we are not looking at a chemical change, we're going to just start with 1 unit, 1 block of chemical energy. Our system is the water vapor, and we know that it's going to stay at the same temperature, so our thermal energy should not change during a phase change, and we're only looking at a phase change in this example. That phase change is taking our gas and turning it into a liquid, and we represent liquids with 2 blocks of phase energy, and of course, no change in chemical energy in this scenario. So we've gone from a total of 8 blocks to a total of 6 blocks, which tells us that energy is leaving the system. Q is going out of the water vapor. And it actually tells us in the question that 4,250 joules of energy specifically is removed. So we can use a very similar equation to our heat of fusion equation. Heat is equal to the heat of vaporization, or energy is equal to the heat of vaporization times the mass of what you are condensing. So we know that 4,250 joules of energy is being removed from the sample or released. We also have a table or a list of important values, heat of vaporization being one of them. So 2,260 joules for every gram of water vapor you have, times the unknown mass. So if we know the amount of energy it took, and we know how much energy it takes per gram, we can solve for the mass by dividing on both sides to get the mass by itself. When we divide those values, we end up with a mass of 1.88 grams of water vapor. And that is how you do a heat of vaporization question.